Right now, the observable universe measures roughly 93 billion light-years from one edge to the other. To cross that distance at the speed of light, the fastest that anything in existence can possibly travel, you would need 93 billion years, which is more than 6 times the entire age of the cosmos itself. And within that almost unimaginable sphere drift nearly 2 trillion galaxies, each one holding somewhere between 100 billion and 1,000 billion stars. Numbers like these are meant to make us feel the grandeur of a universe that seems to stretch on without limit, a cosmos so enormous that exploration of it could continue forever without ever running out of new worlds to find. But that comforting picture is an illusion. The truth hidden beneath it is far stranger and far lonelier than the sheer size of the universe could ever suggest. Here is what will shatter everything you think you know about the cosmos. Nearly everything you can see in the night sky has already slipped beyond your reach forever, and the universe is quietly, patiently, and permanently sealing you inside an ever-shrinking island of light. The galaxies you can observe are not destinations you might someday visit. They are more like the fading echoes of places that have already left, places that are receding from you faster than any ship could ever follow. Faster, in fact, than light itself can travel between them and you. The observable universe is not a frontier waiting to be crossed. It is the wall of a prison whose dimensions you are only now beginning to understand. If you enjoy slow, calming journeys to the farthest edges of physics and the deep future of the cosmos, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these deep dives for you. Make yourself warm and comfortable, let your shoulders drop, and allow the quiet vastness of space to carry you wherever it wishes to go. Let's begin. To understand why nothing can ever escape the observable universe, we first have to understand how human beings ever came to know the size of the universe at all. For almost the entire span of our existence, we had no idea. The sky was a ceiling. The stars were lights fixed to a great dome that turned slowly overhead, and beyond that dome there was either nothing, or there was the realm of the gods, depending on which story your ancestors happened to believe. The idea that those points of light were suns, that they were unthinkably distant, that they were arranged in vast spinning cities of stars separated by gulfs of empty space, all of that would have sounded like madness to almost every human who has ever lived. The first crack in the ceiling came slowly. For thousands of years, the best minds of every civilization measured the heavens with their eyes alone. And the eye is a remarkable instrument, but it has limits. It cannot tell you how far away a light is. A candle held close and a bonfire seen from miles away can look identical. The night sky was a flat painting, and no amount of staring could give it depth. The stars might have been a few miles up, or a few thousand, and there was no way to know the difference. This was the situation for the entire history of astronomy until almost the modern era. Then, in 1610, an Italian named Galileo Galilei turned a small handmade telescope toward the sky from the city of Padua, and the ceiling cracked open. He saw that the faint band of light called the Milky Way, which the ancients had imagined as a river of milk or a road of souls, was not a smooth glow at all. It was made of countless individual stars, far too many and far too faint to ever be separated by the human eye. The number of stars was not a few thousand. It was beyond counting. Suddenly the universe was not a painted dome. It was a place with depth and crowds and distance that no one had ever suspected. But knowing that the stars were many is not the same as knowing how far away they are. That problem would take another 300 years to solve, and the solution would shrink the entire human race down to a speck so small that the men who discovered it could barely bring themselves to believe it. For most of those 300 years, even the most brilliant astronomers believed that the Milky Way was the whole of creation. They thought our galaxy, this single spinning disk of stars, contained everything that existed, surrounded by an infinite empty darkness with nothing in it. The universe in this picture was large, but it was knowable. It had an inventory. You could, in principle, count what was in it. That belief was wrong. Not slightly wrong. It was wrong by a factor so enormous that there is no everyday word for it. And the first person to find the loose thread that would unravel it was a quiet, methodical American astronomer working in the high desert of Arizona, peering at smudges of light that no one else could explain. In the years between 1912 and 1917, an astronomer named Vesto Slipher was working at the Lowell Observatory in Flagstaff, Arizona, a remote outpost built on a mountaintop precisely because the air there was thin and clear and far from city lights. Slipher was studying faint, fuzzy patches in the sky called spiral nebulae. Nobody knew what they were. Some thought they were swirling clouds of gas inside our own galaxy, perhaps young solar systems in the act of forming. Slipher set out to measure their motion, and to do it he used a technique that would become the single most important tool in all of cosmology. He measured their light, and he looked at how the colors within that light were shifted. When an object moves toward you, the light it emits gets squeezed toward the blue end of the spectrum. When it moves away from you, the light gets stretched toward the red end. This is the same effect you hear when an ambulance passes, its siren rising in pitch as it approaches and falling as it recedes, except here it happens with light instead of sound. Slipher measured the colors of these spiral nebulae one by one, painstakingly over years, in the freezing dark of the mountaintop dome. And what he found made no sense at all. Almost every single one of them was shifted toward the red. Almost every single one of them was moving away from us. And they were not moving slowly. They were fleeing at hundreds of kilometers every second, far faster than anything anyone had ever measured in the heavens. Yet a measurement of motion is not a measurement of distance, and this was the wall that astronomy kept running into. Slipher could tell that the spiral nebulae were fleeing, but he could not say how far away they were, and without distance the fleeing meant nothing. A nearby cloud rushing away, and a distant galaxy rushing away, would look almost the same through a telescope. To turn the redshifts into a map of the cosmos, someone first had to find a reliable way to measure the distance to objects so far off that ordinary methods were useless. And the key to that problem had already been found, quietly, years earlier, by a woman whose name almost no one knew. In the years around 1908, at the Harvard College Observatory in Massachusetts, an astronomer named Henrietta Swan Leavitt was studying thousands of variable stars, stars whose brightness rises and falls in a steady rhythm. She was one of a group of women employed to measure and catalogue stars from photographic plates, paid little, granted almost no recognition, and rarely permitted to direct their own research. But Leavitt noticed something extraordinary in a particular class of pulsing stars called Cepheid variables. The brighter ones pulsed more slowly, and the dimmer ones pulsed more quickly, and the relationship between the speed of the pulse and the true brightness of the star was astonishingly precise. This meant that if you simply timed how long a Cepheid took to brighten and dim, you could know exactly how much light it was truly giving off. And if you knew how bright it truly was, and you measured how bright it appeared, the difference told you precisely how far away it must be. Leavitt had discovered a cosmic measuring stick, a way to gauge the distance to anything that contained one of these special stars. It is no exaggeration to say that nearly everything we know about the scale of the universe rests on the foundation she laid. For a time, though, even with this tool in hand, the great question remained fiercely disputed. In 1920, two of the most respected astronomers in America met in Washington for what became known as the Great Debate. On one side stood Harlow Shapley, who argued that the spiral nebulae were relatively small and nearby, mere clouds within our own Milky Way, which he believed contained the entire universe. On the other stood Heber Curtis, who argued that the spirals were vast separate galaxies, island universes in their own right, lying at enormous distances far beyond our own. Both men marshalled their evidence. Neither could prove his case. The matter would only be settled by someone who could find one of Leavitt's measuring sticks inside a spiral nebula itself and read its distance directly. That someone was waiting at the largest telescope on Earth and his measurement would end the debate and shrink the human race in a single night. This was the loose thread. Slipher had the measurements, but he did not yet have the meaning. The meaning would come from a tall, pipe-smoking, deliberately theatrical man working at the largest telescope in the world. In the 1920s, Edwin Hubble was using the great 100-inch telescope at Mount Wilson Observatory, perched above the city of Los Angeles in California. It was the most powerful eye humanity had ever built, and with it, Hubble did something that settled an argument that had divided astronomy for a generation. He found individual stars inside the Andromeda Nebula, and among them he found a special kind of star, a Cepheid variable, whose brightness pulses in a way that reveals its true distance. When Hubble worked out that distance, the result was staggering. Andromeda was not a cloud inside our galaxy. It was another galaxy entirely, an island of hundreds of billions of stars, sitting at a distance so vast that the light arriving in his telescope had left it long before human civilization existed. In a single stroke, the universe expanded from one galaxy to countless galaxies. The Milky Way, which had been the whole of creation, was suddenly revealed as one ordinary city of stars among an uncountable multitude, scattered across a darkness with no known edge. Our home shrank from everything to almost nothing in the span of a single measurement. It is worth pausing simply to feel the size of what Hubble had uncovered, because the numbers resist the imagination. Our own galaxy, the Milky Way, holds somewhere between 100 billion and 400 billion stars. If you tried to count them one at a time, naming a star every second without ever sleeping or resting, it would take you longer than 10,000 years to finish counting the stars in our galaxy alone. You would have begun counting before the invention of writing, before the first cities, before agriculture itself, and you would still not be done today. And the Milky Way is only one galaxy among the nearly 2 trillion that fill the observable universe, each of them holding its own vast multitude of suns. The total number of stars within the cosmos we can see is so large that there are more of them than there are grains of sand on every beach and in every desert on Earth, many times over. This was the universe Hubble revealed when he resolved a single faint smudge into an island of stars. Not a tidy cosmos with an inventory you could take, a cosmos whose contents could never be counted in 100 human lifetimes, stretching out in every direction farther than light itself could carry the news of it. But Hubble was not finished, and his next discovery is the one that matters most for our story. He combined his measurements of distance with the redshift measurements that Slipher and others had gathered, and he noticed a pattern of breathtaking simplicity. The farther away a galaxy was, the faster it was rushing away from us. A galaxy twice as distant fled twice as fast. A galaxy 10 times as distant fled 10 times as fast. This relationship was so clean and so regular that it could be written as a single short rule, and that rule, announced in 1929, changed our understanding of reality forever. The universe was not static. The universe was not a fixed stage on which the stars were arranged. The entire universe was expanding, swelling outward in every direction at once, with every galaxy racing away from every other galaxy. This is the discovery that sets the trap. Because if everything is flying apart today, then yesterday everything was closer together, and the day before that, closer still. Run the film backward, and the galaxies converge. Run it back far enough, and all the matter and energy in the cosmos collapses into a single point of unimaginable density and heat, a beginning from which everything has been expanding ever since. We can measure how fast the expansion is going, and we can measure how far things are, and from those two numbers, we can read the age of the universe directly off the sky. The answer is 13.8 billion years. That is how long ago the expansion began. That is the age of everything. And here is where the strangeness begins to bite. If the universe is only 13.8 billion years old, then light has only had 13.8 billion years to travel. You might reasonably expect that the farthest we could possibly see is 13.8 billion light years in any direction. because light from anything farther away would simply not have had enough time to reach us yet. But that is not what we find. The edge of the observable universe lies not at 13.8 billion light-years, but at roughly 46 billion light-years in every direction. The light that left those most distant regions began its journey near the dawn of time. But while that light was travelling toward us, the space it was crossing was stretching. The galaxies that emitted it have been carried much farther away by the expansion of space itself. We see the light from where they were. We can never reach where they are. The very oldest light that reaches us has a name and a story, and it is the most direct proof we possess that the universe was once small, hot and dense. To find it, we have to go back to a small town in New Jersey and to one of the great accidents in the history of science. In 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to use a large horn-shaped antenna to study faint radio signals from the sky. Their names were Arno Penzias and Robert Wilson, and they had a problem. No matter where they pointed their antenna, no matter the time of day or the season of the year, they detected a faint persistent hiss, a background static that would not go away. They assumed it was a fault in their equipment. They checked every connection. They cooled their detectors. They even climbed inside the great horn and scraped out the droppings of pigeons that had been roosting there, suspecting the white residue might be the source of the noise. Nothing helped. The hiss remained, coming from every direction in the sky at once, as though the entire cosmos were quietly glowing. It was. What Penzias and Wilson had stumbled upon, without looking for it, was the afterglow of the Big Bang itself. In the first few 100,000 years after the beginning, the universe was so hot and dense that it was a glowing fog, an opaque sea of charged particles through which light could not travel freely. Then, after roughly 380,000 years, the universe expanded and cooled just enough for the particles to combine into neutral atoms, and the fog suddenly cleared. Light was set free to travel across space for the first time, and it has been traveling ever since. This is the moment cosmologists call recombination, the instant the universe became transparent, and the light released at that moment has been crossing the cosmos for nearly the entire history of time. If you could have been present at the moment of recombination, the entire sky in every direction would have glowed a deep, dull red, like the inside of an enormous furnace cooling slowly toward darkness. That ancient light is still arriving today, but it does not look red anymore, and the reason it has changed is the whole secret of our story. As that light crossed the expanding universe for nearly 14 billion years, the space it travelled through stretched, and the light stretched with it. Its waves were pulled longer and longer, sliding down out of visible light, through infrared, all the way into the microwave band. The fiery red glow of the young universe has been cooled and stretched by the expansion of space into a whisper of microwave static, the temperature of which is now only 2.7 degrees above absolute zero. This is the hiss that Penzias and Wilson could not silence. It fills all of space. It is the oldest thing we can ever see, the literal edge of the observable universe, the wall of fog beyond which no light can reach us, because beyond it the universe was opaque. And it is also a warning written in the sky, because the same stretching that turned that fire into a whisper will, given enough time, stretch it away entirely. Even this most ancient and pervasive of all signals will be redshifted into silence and erased from the reach of any future observer. This is the crushing truth that the size of the universe was hiding all along. The 93 billion light-years across that we began with is not the width of a place you could explore. It is the width of a memory. The light reaching your eyes tonight is ancient, a fossil glow from objects that have already fled far beyond the point where any signal you could ever send would catch them. The map of the universe is real, but it is a map of the past, and the territory it describes is already gone. This is the disturbing reality of cosmic expansion, and to understand why it works the way it does, we have to dismantle one of the most stubborn misunderstandings that almost everyone carries about the beginning of the universe. Ask most people what the Big Bang was, and they will describe an explosion, a bomb of matter detonating somewhere in the dark, hurling stars and galaxies outward into the empty space that surrounded it, like shrapnel flying away from a blast. It is a vivid image. It is also completely wrong. Not slightly wrong, fundamentally wrong, in a way that changes everything about how we have to think about distance, motion, and escape. The Big Bang was not an explosion in space. It was an expansion of space. There was no empty room waiting for the galaxies to fly out into. There was no center from which everything was thrown. And there is no edge where the debris finally thins out. The expansion did not happen at a point inside the universe. The expansion happened everywhere, all at once, to all of space simultaneously, and it is still happening right now. In the space between you and these words, in the space between the Earth and the Moon, in the space between every galaxy and every other galaxy across the entire cosmos. Space itself is not the empty stage on which the cosmic drama plays out. Space itself is the thing that is growing. Understanding why requires dismantling everything you think you know about how things move. When you walk across a room, you move through space. Your position changes relative to the floor, the walls, the air. This is motion in the ordinary sense, and it obeys the ordinary rules, including the most famous rule of all, the cosmic speed limit. Nothing can move through space faster than light. This is one of the most thoroughly tested principles in all of science, confirmed in every laboratory and every particle accelerator on Earth. If a galaxy were truly flying away from us through space, then its speed could approach the speed of light, but it could never reach it or exceed it. And yet the most distant galaxies we observe are receding from us at speeds far greater than light. Some of them are pulling away at twice the speed of light, some at 3 times. How can this be allowed? The answer is that they are not moving through space at all. They are very nearly still in their own neighborhoods, drifting only gently, exactly as our own galaxy drifts gently in ours. What is happening is that the space between us and them is expanding, swelling, multiplying, adding more distance in every direction with every passing moment. The galaxies are not running away. The road between us is lengthening. And there is no speed limit on the lengthening of the road. The cosmic speed limit governs motion through space. It says nothing whatsoever about how fast space itself may grow. This single distinction is the key that unlocks the entire mystery, and it is the reason that escape from the observable universe is not merely difficult, but mathematically impossible. To make this tangible, imagine an enormous loaf of raisin bread rising in an oven. The raisins are the galaxies, the dough is space. As the dough rises, it expands in every direction, and every raisin moves away from every other raisin. Not because the raisins are swimming through the dough, but because the dough between them is growing. Now here is the crucial part. A raisin near you drifts away slowly, because there is only a little dough between you and it, and only a little dough is being added. But a raisin on the far side of the loaf recedes from you very quickly, because there is an enormous amount of dough between you and it, and all of that dough is expanding at once. The farther the raisin, the faster it flees, and not because it is moving faster, but because there is more growing space in between. This is precisely the pattern that Hubble discovered. The recession speed grows with distance, without limit, until at some distance the dough between you and a faraway raisin is being added so fast that the raisin recedes faster than any signal could ever cross the gap. The mathematics of this become even more remarkable when you put real numbers to them. For every megaparsec of distance, a span equal to roughly 3 million light-years, the expansion of space carries galaxies apart at an additional 70 kilometers per second. That sounds gentle, and at close range it is. A galaxy a few million light-years away barely seems to move. But the effect compounds with distance relentlessly. By the time you reach a galaxy 14.5 billion light-years away, the accumulated stretching of all that intervening space carries it away from us at the full speed of light. This particular distance has a name. It is called the Hubble radius, and it marks the threshold where recession reaches light speed. Beyond it, Galaxies recede faster than light, and the observable universe extends far beyond that threshold, all the way out to 46 billion light-years, which means that the overwhelming majority of the galaxies we can see are already receding from us faster than light can travel. Consider what this means. When you look up at one of these distant galaxies, you are looking at light that left it billions of years ago, when both it and the space around it were arranged very differently. While that light crawled across the widening gulf, the gulf kept widening underneath it, like a swimmer struggling toward a shore that drifts steadily backward. The light made progress, but the finish line retreated. For the most distant light we can see, the very oldest glow in the cosmos, the journey took more than 13 billion years, and it crossed what is now a gap of 46 billion light-years. The road kept growing while the messenger was still upon it. The image is genuine. The object it depicts is real. But the gap between the image and the object can never be closed by anything. Not by light, not by radio, not by any vessel we could ever conceive. This was almost too strange for the people who first worked out the equations. The framework that describes it came from Albert Einstein, who in 1915 completed his general theory of relativity, a description of gravity not as a force pulling objects together, but as the bending and stretching of space and time themselves. Einstein's equations, when applied to the universe as a whole, refused to hold still. They insisted that the cosmos must either be expanding or contracting, never static. This troubled Einstein so deeply that in 1917 he inserted an extra term into his own equations, a fudge factor he called the cosmological constant. It was designed to hold the universe still and unchanging, because a static eternal universe was what he and almost everyone else believed in. He forced the mathematics to lie, because the truth it was telling him seemed too radical to accept. Then a Russian mathematician named Alexander Friedmann, working in 1922, took Einstein's equations at face value and showed that they naturally described an expanding universe with no fudging required. And a Belgian priest and physicist named Georges Lemaitre, working independently in 1927, reached the same conclusion and then went further. He proposed that if the universe was expanding now, then it must have begun from a single primeval atom, a dense hot origin from which all space and time unfurled. When Hubble's observations confirmed the expansion at the end of that decade, Einstein abandoned the cosmological constant entirely and reportedly called it the greatest blunder of his life. He had been so close to predicting the expansion of the universe from pure mathematics, years before anyone measured it, and he had flinched. The equations had been braver than the man who wrote them. Here is the part that should make the hair stand up on the back of your neck. That so-called blunder, the cosmological constant that Einstein threw away in embarrassment, was not a mistake at all. Decades later it would come roaring back, not as a tool to hold the universe still, but as the engine driving it apart faster and faster, the very force that turns the observable universe from a frontier into a sealed and shrinking cell. But that is a discovery from the far end of the 20th century, and to feel its full weight, we first have to understand the difference between what we can see and what we can ever touch, because they are not the same boundary, and the gap between them is where the prison walls truly stand. This distinction matters enormously, because there are two different edges to the universe, and almost everyone confuses them. The first edge is the one we have been describing, the boundary of what we can see. It is called the particle horizon, and it sits at 46 billion light-years away. Everything inside it has had time, over the whole history of the cosmos, to send at least some ancient light into our eyes. Everything beyond it is invisible, not because it does not exist, but because its light has simply not had enough time to reach us yet. The particle horizon is the edge of the seeable, and in a static universe, or even a gently coasting one, that edge would keep expanding outward forever, revealing more and more of the cosmos as the eons passed, like a sunrise slowly illuminating a vast dark landscape. But there is a second edge, and it is the one that closes the trap. It is called the cosmic event horizon, and it has nothing to do with what we can see. It has to do with what we can reach. The event horizon is the boundary beyond which nothing we do now can ever have any effect, ever, for the rest of time. If you sent a beam of light toward a galaxy that lies beyond the event horizon, that beam would travel outward forever and never arrive. The galaxy is receding so quickly, carried by the expansion of all the space in between, that even light aimed directly at it loses the race. The light moves toward the galaxy at the speed of light, and the space between them grows faster than the light can close it. The galaxy is not merely far away, it is causally severed from us, cut off from any possible future contact, locked outside a door that can never be reopened. To appreciate how strange this truly is, consider the difference between these two horizons. The particle horizon contains everything we can observe, all 2 trillion galaxies, stretching out to 46 billion light-years. The event horizon, the boundary of everything we could ever touch or influence or visit, sits much closer, at roughly 16 billion light-years away. The space between those two numbers contains the great tragedy of cosmology. It is full of galaxies we can see in perfect detail, galaxies whose light fills our most powerful telescopes, galaxies that are demonstrably, gloriously real, and yet not a single one of them can ever be reached by us, nor we by them. We can watch them, we can never wave back. They are like faces in old photographs of people who died long ago, present to the eye, gone beyond any reunion. When you do the accounting, the result is almost unbearable. Of all the galaxies we can currently observe, only about 3% lie within the event horizon, within the realm we could ever in principle visit, even travelling at the speed of light from this very moment forward. The other 97% are already lost. They are visible, but unreachable, glowing on our screens while drifting permanently beyond our grasp. If humanity launched a fleet of ships at the speed of light tonight, and those ships travelled outward for the entire remaining age of the universe and beyond, they would still only ever reach that small 3%. The rest of everything we can see is a museum behind glass. We may look, we may never enter. And every day, quietly, more of it slips from the reachable into the merely visible, and from the visible into the gone. There is one more idea we must hold clearly in mind, because it changes the meaning of the word edge entirely. The observable universe is not a place with a wall standing at the boundary of all existence. It is simply the limit of what we, from our particular vantage point, can see and reach. An observer in one of those distant galaxies, billions of light years away, would see their own observable universe, a sphere of the same size centered on themselves. It would reach out in every direction to their own horizon, much of which would lie in regions completely invisible to us. Every observer everywhere sits at the center of their own private bubble of the cosmos, and no two bubbles are quite the same. There is no true center to the universe, and there is no single edge. There are only horizons, one for every point in space, each one a limit not of the cosmos itself, but of what can be known from where you happen to stand. This means the universe almost certainly does not end at the boundary of what we can see. Beyond our horizon, the same kind of space continues, filled with the same kind of galaxies, very likely stretching on far beyond the 46 billion light years we can observe, perhaps without any end at all. The honest answer is that we do not know whether the universe as a whole is finite or infinite. We can only ever measure our own bubble, and our bubble looks the same in every direction and shows no sign of an edge. So the wall that seals us in is not the boundary of reality, it is the boundary of our reach. The cosmos beyond it is real, and vast, and quite possibly endless, and we are cut off from all of it, not because it does not exist, but because the expanding space between us and it can never be crossed. We are sealed not inside the universe, but inside our small luminous corner of it, while the true universe stretches on, unknowable, in every direction, forever. Now you might wonder how we can be so certain that this is permanent. Perhaps the expansion is slowing down. Perhaps gravity, the great attractive force that binds galaxies and clusters together, is gradually applying the brakes to the whole cosmic expansion, and someday the galaxies will slow, stop, and begin to fall back together. For most of the 20th century, this was exactly what cosmologists expected to find. The only question seemed to be whether the universe had enough matter in it to eventually halt the expansion and reverse it, or whether it would expand forever but always at a slowing rate. Everyone agreed that gravity must be pulling the brakes. The only debate was about how hard. The idea that the expansion might be speeding up was not even on the table. It would have seemed absurd. Then came 1998, and one of the most stunning reversals in the history of science. Two competing teams of astronomers set out to measure exactly how much the expansion was slowing down. One team was led by Saul Perlmutter at the Lawrence Berkeley National Laboratory in California. The other included Brian Schmidt and Adam Rees, working across observatories in Australia and the United States. Both teams used the same elegant tool, a particular kind of exploding star called a Type Ia supernova. These stars detonate with almost exactly the same brightness every time, which makes them perfect cosmic mile markers. By measuring how bright a distant supernova appears, you can work out how far away it is. By measuring its redshift, you can work out how fast the space around it has been stretching. Compare enough of them across enough of cosmic history, and you can read the entire expansion rate of the universe, past and present, directly from the light of dying stars. They expected to measure the deceleration. What they found instead stopped them cold. The distant supernova were fainter than they should have been. They were farther away than a slowing universe could account for. The expansion was not braking at all. It was accelerating. It had been slowing for billions of years under the pull of gravity. And then, around 6 billion years ago, something had flipped, and the expansion had begun to speed up, faster and faster, pushing the galaxies apart at an ever-increasing rate. Both teams checked their results again and again, terrified of announcing something so heretical and being wrong. But the data would not budge. The universe was being torn apart by an unknown force that filled all of empty space, a force pushing outward against gravity and winning. They had no idea what it was, so they gave it a name that was really just a confession of ignorance. They called it dark energy. It is worth pausing on how strange that moment of discovery truly was for the people who lived it. The two teams of astronomers were rivals, racing each other, each suspecting the other might be ahead, and both of them expecting to confirm the same comfortable result that the universe was slowing down. When the numbers first came back showing acceleration instead, the natural assumption was that something had gone wrong. Perhaps the distant supernovae were intrinsically dimmer in the early universe. Perhaps dust between the galaxies was absorbing their light and making them seem farther away. Perhaps there was an error in the calibration. The researchers spent months chasing every possible mistake, precisely because the result was so unwelcome and so revolutionary. Adam Rees, then a young scientist, later described the unease of staring at data that insisted on something he did not want to believe. But every check confirmed it. The supernovae were genuinely too faint. The expansion was genuinely speeding up. In 1998, both teams published, and within a few short years the entire field of cosmology had been overturned. In 2011, Saul Perlmutter, Brian Schmidt and Adam Rees shared the Nobel Prize in Physics for the discovery. A discovery none of them had set out to make, and all of them had initially resisted. The reason their finding seals the prison so completely lies in how the event horizon is reckoned. The horizon is not a fixed wall built into the universe. It is a balance point. The distance at which the outward stretching of space exactly matches the inward crawl of light. The place where a beam of light heading toward us makes no net progress, because the road beneath it lengthens just as fast as the beam advances. In a universe slowing down, that balance point would drift outward over time, and more of the cosmos would gradually come within reach. But in a universe speeding up, the balance point drifts inward. The faster space expands, the closer the horizon creeps, and the more galaxies fall outside it. This is why the discovery of acceleration was not merely a curiosity about distant supernovae. It was the discovery that the door is not standing open and slowly admitting more of the cosmos as everyone had assumed. The door is swinging shut. And because dark energy does not weaken as space grows, the door will keep swinging shut forever, at an ever-quickening pace, until almost nothing remains within reach but the galaxy we already inhabit. The mathematics become even more disturbing when you trace where this leads. If the expansion is merely steady, then the event horizon stays roughly where it is, and the situation, though grim, is at least stable. But the expansion is not steady, it is accelerating, which means the event horizon is not standing still, it is closing in. Every year, galaxies that were once within our reach cross the threshold and become permanently unreachable. Every year, the door swings a little further shut. The acceleration guarantees that this process can never reverse, because dark energy does not dilute as the universe grows. Ordinary matter spreads thinner as space expands, its influence fading. But dark energy is a property of space itself, and the more space there is, the more dark energy there is to push it apart. The expansion feeds on its own product. The faster it goes, the faster it goes. This is the profound truth that Einstein's discarded equation encodes but everyday experience obscures. The cosmological constant he threw away in shame was real after all. It was the dark energy, the relentless pressure of the vacuum, the force that ensures the observable universe is not a frontier, but a closing aperture. He had glimpsed it in 1917, recoiled from it, and called it his greatest blunder. He died in 1955, more than 4 decades before the supernova teams proved that his blunder had been one of his deepest insights. The universe really did contain a term that pushed space apart. He simply had the direction of history wrong. He thought it held the cosmos still. In truth, it is prying the cosmos open, wider and faster, sealing each of us inside a bubble of reachable space that grows lonelier with every passing eon. And the loneliness, as we are about to see, has a deadline. Here is the problem that the acceleration creates, and it is a problem not of space but of time. We have spoken so far as though the distant galaxies will simply remain forever beyond reach, frozen in our telescopes like insects in amber, visible but untouchable. But that is not what happens. They do not stay, they fade. As the expansion accelerates, and the space between us and a distant galaxy stretches faster and faster, the light from that galaxy is stretched along with it. The waves of light are pulled longer and longer, sliding down from visible colors into infrared, then into microwaves, then into radio waves of enormous length, growing fainter and dimmer, and more stretched at every step. Eventually the light is stretched so far that no instrument could ever detect it. The galaxy does not move out of the sky, it dims out of existence, redshifted into invisibility, erased from the observable universe not by going anywhere, but by the road to it growing infinite. There is something uncanny about the way a galaxy disappears across this boundary, and it is worth lingering on, because it does not vanish the way we might expect. It does not simply wink out, nor does it sail smoothly off into the distance and shrink to a point. Instead, as a distant galaxy approaches the event horizon, its light is stretched and dimmed more and more severely, and the image of it appears to slow, to redden, and to freeze. The closer it drifts toward the horizon, the more its light is drained of energy, and its motion seems to stall, until the galaxy hangs there, fading and reddening, its final moments stretched out across an eternity of our time. In a strange and exact way, this is the same thing that happens when an object falls toward a black hole. To a distant watcher, the falling object never quite seems to cross the edge. It slows, it reddens, its light grows fainter and fainter, and it appears to freeze forever at the threshold. The galaxies leaving our cosmos do the same. They do not so much depart as fade in place. Their last light stretched thinner and thinner until it slips below anything we could ever detect. Frozen images of places that have, in truth, already gone. What we lose is not the sudden disappearance of a light, but the slow, silent reddening of a face that never quite finishes leaving, and yet is already beyond all return. Consider what this means for the deep future. Right now, when we look out into the cosmos, we see a sky crowded with galaxies in every direction, a glittering census of 2 trillion island universes stretching back almost to the beginning of time. But this is a temporary view. We happen to be alive during a brief, privileged window when the universe is still young enough, and the expansion still gentle enough, that the light of distant galaxies can still reach us. That window is closing. As the eons pass, one by one, the galaxies will redshift past the point of detectability and vanish. The sky will empty out, slowly at first, then with gathering speed, until at last there is nothing left to see beyond our own immediate cosmic neighborhood. That neighborhood has a name. It is called the local group, a small cluster of galaxies bound together by their mutual gravity. Our Milky Way is its largest member, alongside the Great Spiral of Andromeda and a few dozen smaller galaxies orbiting them both. Because these galaxies are bound to one another by gravity, the expansion of space cannot pull them apart. Inside a gravitationally bound system, the local pull is stronger than the cosmic stretch, and so the local group holds together as a stable island even as the rest of the universe flies away. In fact, Andromeda is not receding from us at all. It is approaching, drawn by gravity, and in roughly 4 billion years it will collide and merge with the Milky Way, the 2 great spirals slowly winding together over hundreds of millions of years into a single vast elliptical galaxy. Astronomers have already given this future galaxy a name. They call it Milkdromeda. To feel how this isolation will unfold, picture the night sky over an unimaginably distant future and the slow merging of our own galaxy with its great neighbor. Andromeda is the nearest large galaxy to our own, a spiral of perhaps 1 trillion stars, and it is not fleeing from us. It is falling toward us, drawn across the gulf by gravity, approaching at roughly 110 kilometers every second. In about 4 billion years, the 2 galaxies will begin to collide, though the word collide is misleading, because the stars themselves are so far apart that almost none of them will ever strike one another. Instead, the 2 great spirals will pass through each other, their shapes torn and stretched by gravity, throwing long streamers of stars out into the dark. Then they will fall back together, pass through again, and over hundreds of millions of years slowly settle into a single enormous elliptical galaxy. The delicate spiral arms that define both galaxies will be gone, replaced by a featureless, smooth swarm of stars. Astronomers have named this future galaxy Milkdromeda, and it will be the home of whatever remains of our cosmic neighborhood. Now stand on an imagined world inside that merged galaxy, in an epoch perhaps 100 billion years from now, and look up. The sky will be unrecognizable. There will be no band of the Milky Way arching overhead, because the structure that made that band will have been gently rearranged into the smooth swarm of the elliptical. The stars will still be there, scattered across the dark in their thousands, close and warm and familiar. But beyond them, there will be nothing at all. No faint smudge of a neighboring galaxy, no distant clusters glittering at the very edge of vision, no band of light from anything beyond the local stars, because every other island of the cosmos will have receded past the horizon and dimmed into a blackness without any feature whatsoever. The night will be deeper and emptier than any night that has ever fallen on Earth, a darkness pressing right up against the outermost stars, with not a single distant light to suggest that anything lies beyond. And the beings who gaze up into that perfect starless void will have no reason to imagine that it was ever filled. They will never know that the same emptiness once blazed with 2 trillion galaxies, that the sky they take for eternal was once the richest spectacle in all of creation. This merged galaxy, and the handful of small companions that remain bound to it, will be the entire universe for any beings that exist in the far future. Everything else will be gone. Estimates suggest that in roughly 150 billion years, perhaps 200 billion, every galaxy outside our own local group will have receded beyond the event horizon and redshifted into total invisibility. The night sky of that distant epoch will contain the stars of our own galaxy, and nothing else. No Andromeda, because it will have merged into us. No distant spirals, no faint smudges of light from other islands, no faraway clusters, just our own stars, and beyond them, a perfect, featureless, eternal black. Now extend that perspective across deep time, and the consequence becomes genuinely chilling. Imagine an intelligent civilization arising in that far future, hundreds of billions of years from now, on some world orbiting a star in the merged remnant of our galaxy. These beings build telescopes. They study the heavens with the same curiosity and rigor that drove Slipher and Hubble and the supernova hunters. And they find nothing. They look out, and they see only their own galaxy, a single island of stars surrounded by an apparently infinite and empty void. There are no other galaxies to measure. There is no redshift to discover, because there is nothing left to be redshifted. The cosmic background glow, the ancient light from the Big Bang that we detect so easily today, will itself have been stretched to wavelengths longer than the observable universe and washed out below any possible detection. To these future astronomers, the universe will appear to be exactly what Einstein once wished it to be: static, eternal, unchanging, a single galaxy floating alone in a darkness, with no beginning and no end. They will be wrong, of course, in precisely the way that the astronomers of a century ago were wrong, when they believed the Milky Way was everything. But here is the devastating difference. The astronomers of a century ago were wrong, because they had not yet looked closely enough, and the evidence was waiting to be found. The astronomers of the far future will be wrong, because the evidence will no longer exist. The expansion will have carried it away. The Big Bang will have left no detectable trace. The other galaxies will be not merely too faint to see, but causally erased, beyond any horizon, in a realm from which not one photon can ever again arrive. These future beings could be flawless scientists, perfectly rigorous, and they would still conclude that they live in a static, solitary, eternal cosmos, and there would be no observation they could ever make to correct the error. The truth would be unreachable, not because they failed, but because the universe had hidden it. This realization was laid out in detail by two physicists, Lawrence Krauss and Robert Scherer, in a paper published in 2007, with the haunting observation that we are living in a unique moment in cosmic history. We arrived early enough to see the evidence of our origins still written across the sky. We can detect the expansion. We can measure the background radiation. We can map the 2 trillion galaxies and read the story of where we came from. A civilization arriving too late would have none of this. The book of cosmic history is being slowly erased, page by page, galaxy by galaxy, and we happen to be reading it during the brief interval before the words fade. The honest and unsettling conclusion is that there may already be features of the universe that have been erased before we ever arrived. Truths that were observable to some hypothetical earlier observer and are now gone forever. They lie beyond our horizon, lost in the same way that the distant galaxies will one day be lost to our descendants. There is a strange and quiet grief in this. We tend to imagine that knowledge accumulates, that the universe is a puzzle slowly being solved, that each generation sees a little farther than the last, and that this progress could continue without limit. But cosmology reveals that the opposite is also true. The window of what can be known is not only opening. In the largest sense, it is closing. The cosmos is becoming less knowable, not more, as the connections between its parts are severed one after another by the expansion of empty space. We are not standing at the dawn of an endless age of discovery. We are standing in a clearing in the fog, a clearing that is slowly contracting, and we are fortunate beyond measure to be standing in it at all, because the view from here will never be this complete again. And yet, even this is not the deepest layer of the problem, because so far we have spoken of dark energy as a known force, a measured fact, a thing we have detected and named. But the truth is that we named it precisely because we do not understand it. We can see what it does. We have no idea what it is. And when we look closely at the mathematics of the vacuum, at the empty space that this force seems to inhabit, we find a discrepancy so vast, so absurd, so far beyond any error ever made in the history of science. Some physicists have called it the single most embarrassing prediction in all of physics. The thing that is sealing us inside the observable universe is not just powerful, it is at the deepest level a complete mystery. To understand the depth of that mystery, we have to ask what dark energy actually is. And the most natural answer takes us straight back to Einstein's discarded term. The simplest explanation for the accelerating expansion is that empty space is not empty. According to our best theories of the very small, the vacuum, the most perfect emptiness you could ever imagine, with every atom and every particle removed, is not truly nothing. It seethes with activity at the smallest scales, with pairs of particles flickering into existence and vanishing again faster than any clock could measure, borrowing energy from the vacuum and paying it back instantly. This restless quantum foam gives empty space itself a faint intrinsic energy, an energy that belongs not to any object within space, but to space itself. And this vacuum energy would push outward, exactly like Einstein's cosmological constant, exactly like the dark energy we observe. The picture is elegant. Empty space has energy. That energy drives expansion. As the universe grows, it creates more empty space, which carries more vacuum energy, which drives the expansion harder still. It explains everything we see. There is only one problem, and it is a problem of a magnitude almost beyond comprehension. When physicists try to calculate how much energy the vacuum should contain, using the same quantum theories that work flawlessly in every other context, they get an answer that is wrong. Not slightly wrong. Wrong by a factor that staggers the imagination. The predicted energy of the vacuum is larger than the measured value, by a number with roughly 120 zeros after it. To write that mismatch out in full, you would need a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation anywhere in all of science, a failure so total that physicists do not really regard it as an approximation that is a little off. They regard it as a sign that something fundamental is missing from our understanding of reality. Think about what that means. The force that is sealing us into our shrinking island of the cosmos. The force that will one day erase every other galaxy from the sky. The force that determines the entire long-term fate of all existence. It is something we can measure to fine precision, and yet cannot explain by a margin of 120 orders of magnitude. We know it is there. We know what it does. We have no working theory of why it has the strength it has, rather than being vastly larger and tearing every atom apart, or vastly smaller and irrelevant. The honest answer is that nobody knows. Some of the most brilliant minds alive have spent their careers on this question and come away empty-handed. The architecture of our cosmic prison is built from a material whose composition we have not begun to understand. The depth of our ignorance about dark energy is difficult to overstate, and it is worth dwelling on, because the thing that determines the fate of all existence is something we cannot derive, predict, or explain. When physicists use quantum theory to calculate the energy that should reside in empty space, they do not get a number that is merely too large by a comfortable margin. They get a number that exceeds the measured value by a factor with about 120 zeros after it. If the vacuum truly held that much energy, the expansion would have been so violent that space would have torn itself apart in the first instant, and no galaxies, no stars, and no observers could ever have formed. The fact that the universe is gentle enough to permit our existence, that the cosmological constant is so extraordinarily, delicately small rather than catastrophically large, is one of the great unsolved puzzles of modern physics. Something must be cancelling that enormous predicted energy almost perfectly, to more than 100 decimal places, leaving behind only the faint residue that we measure as dark energy. We do not know what does the cancelling. We do not know why the residue has the precise value it does. We only know that if it were much different, we would not be here to wonder about it. That last observation has led some physicists down a strange and controversial road. In 1987, the physicist Steven Weinberg made an argument that, given how finely tuned the cosmological constant appears to be, perhaps it takes the value it does, simply because only in universes where it is small can observers exist to measure it. This kind of reasoning, sometimes called the anthropic principle, becomes meaningful only if there are vast numbers of universes with different values of the constant, a so-called multiverse, of which we necessarily inhabit one of the rare hospitable members. It must be said clearly that this idea is deeply speculative. There is no direct evidence for other universes, and by their very nature they would lie beyond any horizon we could ever observe, which makes the proposal difficult, or perhaps impossible to test. The honest answer is that nobody knows whether a multiverse exists, and many physicists regard the idea with serious skepticism. But the fact that some of the most careful thinkers in the field have been driven to such radical speculation is itself a measure of how profoundly the dark energy puzzle resists every ordinary explanation. Whatever its origin, the long-term behavior of this energy is what fixes the destiny of the cosmos. As matter continues to thin out and dark energy comes to dominate completely, the expansion approaches a pure exponential, the form first studied by the Dutch astronomer Willem de Sitter in 1917. A de Sitter universe is an eerie thing. Every observer within it sits at the center of their own horizon, a fixed sphere beyond which nothing can ever reach them, identical in size for everyone, everywhere, for all time. The universe becomes a landscape of isolated bubbles, each one a pocket of reachable space surrounded by an impenetrable wall of expanding emptiness. Each one shrinks in content as its galaxies redshift away, until it holds only the bound matter that gravity has managed to keep together. This is the geometry toward which our universe is relentlessly settling, not a chaos of explosion, but a smooth, silent, mathematically inevitable drift into separation, in which every island of matter ends alone inside a horizon it can never cross, and that nothing can ever cross to reach it. But let us set aside the question of what dark energy is, and follow instead the question of what it does, because its long-term behavior is what truly closes the trap. Ordinary matter, the stuff of stars and planets and people, thins out as the universe expands. Spread the same amount of matter across a larger and larger volume, and its density falls. The gravitational pull of matter, which once dominated the cosmos and slowed its expansion, grows weaker and weaker as the galaxies are diluted across ever greater volumes of space. Dark energy does the opposite. Because it is a property of space itself, its density never falls. Every cubic meter of space carries the same dark energy it always did, and as expansion creates new cubic meters, it creates new dark energy along with them. There is simply more and more of the stuff, while matter fades toward nothing. This guarantees a particular destiny. There was an early era when matter was dense and dominant, and its gravity slowed the expansion. We saw the fingerprint of that era in the supernova data, the long deceleration before the turning point. Then, as matter thinned and dark energy held steady, there came a crossover, around 6 billion years ago, when dark energy overtook matter and the expansion began to accelerate. And from here forward, the trend only sharpens. Matter will continue to dilute toward irrelevance, while dark energy holds firm and comes to dominate completely. When that happens, the expansion settles into a particular mathematical form, a relentless exponential growth, where every region of space doubles in size over a fixed interval, and then doubles again, and again, forever. Physicists call this a de Sitter universe, after the Dutch astronomer Willem de Sitter, who first explored these solutions to Einstein's equations in 1917, in the very same year that Einstein was busy inventing the cosmological constant to avoid them. Exponential expansion is the mathematics of a runaway process, and it is utterly merciless to any hope of escape. Consider what it does to the event horizon. In a universe expanding exponentially, the event horizon does not retreat as you approach it. It stays at a fixed distance ahead of you, like a wall you can never reach no matter how far or how fast you travel. Suppose you launched a ship at nearly the speed of light toward the edge of the reachable universe. As you traveled, space behind you and ahead of you would keep doubling, and the horizon would keep pace with you, always 16 billion light years away, always just beyond the reach of your fastest possible vessel. You could travel for 1 trillion years. You could travel for the entire future history of the cosmos. And the boundary would remain exactly as far away as when you started. This is why nothing can ever escape the observable universe. Not because the walls are too far, because the walls move faster than anything that chases them, and they will do so forever. And do not imagine for a moment that our machines come anywhere close to challenging these distances. Consider the fastest objects human beings have ever built. The Voyager 1 spacecraft, launched in 1977, has been travelling outward for almost half a century, and it is the most distant human-made object in existence, now drifting in interstellar space beyond the edge of our solar system. It moves at roughly 61,000 kilometers per hour, a speed that would carry it around the entire Earth in well under an hour. And yet, at that velocity, it would take more than 70,000 years just to reach the nearest star to our Sun, a star that sits practically next door on the cosmic scale. If the journey to that neighbouring star were shrunk down to the length of a walk across a single room, Voyager 1, after nearly 50 years of flight, would have covered a distance smaller than the width of a human hair. The fastest probe we have ever launched, the Parker Solar Probe, reaches far greater speeds as it dives toward the Sun, hundreds of thousands of kilometers per hour. And even it would need thousands of years to reach the nearest star, and longer than the present age of the universe to cross our own galaxy a single time. To appreciate how hopeless escape truly is, consider what it would take to reach not the nearest star, but the nearest galaxy beyond our own. The energy required to accelerate even a small ship to a speed great enough to cross such distances within a human lifetime is almost beyond comprehension. Not the energy stored in a tank of rocket fuel, not the energy released by every nuclear weapon ever built, not the energy our entire civilization produces in a century. To push a single modest vessel across intergalactic space at any meaningful fraction of the speed of light would demand a quantity of energy that dwarfs the total output of the Sun over years. And to do it before the target galaxy itself crossed the event horizon would demand the impossible, a chase against an opponent that grows faster the longer it runs. This is the deepest face of the trap. It is not merely that the galaxies are far, it is that the laws of physics conspire at every level, in the speed of light, in the cost of acceleration, in the relentless growth of the space between, to make the gap uncrossable not by a little, but by an overwhelming and permanent margin. The mathematics become even more striking when you realize how the event horizon resembles another object that physicists know intimately. A black hole also has an event horizon, a boundary past which nothing, not even light, can ever return. Fall past the event horizon of a black hole, and no signal you send can ever climb back out. The cosmic event horizon is, in a deep sense, the same kind of boundary turned inside out. With a black hole, you are outside, and the horizon traps things within. With the cosmos, you are inside, and the horizon traps you within. The galaxies receding beyond the cosmic horizon are crossing a one-way membrane every bit as absolute as the edge of a black hole, except that there is no falling involved. They simply drift, gently, as the space between expands, and at some quiet, unmarked moment they pass a line beyond which they can never again be reached, and neither they nor we will feel a thing as it happens. What comes next will fundamentally alter how you think about the future of everything, because the same dark energy that seals our horizon also writes the final chapters of cosmic history, and those chapters are long beyond any human sense of time. There are a few possible endings, and physicists weigh them carefully. The most likely is a slow, cold dimming, in which the universe simply keeps expanding and cooling forever, the galaxies isolating, the stars burning out, the cosmos sliding toward a final featureless equilibrium. A second possibility, less likely but not ruled out, is far more violent. If dark energy is not perfectly constant, if its strength should grow with time rather than holding steady, then the expansion would not merely accelerate but accelerate without bound. It would eventually tear apart not just galaxies but stars, then planets, then atoms, then the very fabric of space, in a catastrophe called the Big Rip. And a third possibility, now considered remote, is that dark energy could someday weaken or reverse, allowing gravity to reclaim the cosmos. But every measurement we have points toward the steady, the relentless, the patient version, the version where nothing is torn and nothing escapes, and the universe simply grows colder and emptier and more silent across spans of time that make the current age of the cosmos look like a single heartbeat. The honest truth is that we do not know which ending awaits, because we do not know what dark energy truly is, and its deepest nature determines its ultimate behavior. But all the leading possibilities share one feature. In none of them does the observable universe ever open back up. In none of them do the lost galaxies ever return. The expansion has set a direction, and that direction is toward greater isolation, greater silence, greater dark. And to feel the full weight of where that direction leads, we have to follow it all the way to the end, to the last stars, the last light, and the final, almost unimaginable stillness that the equations promise lies at the far end of time. To walk to the end of time, we have to abandon every unit of measurement that human life has ever used. Years, centuries, the age of civilizations, even the age of the universe itself. All of these become vanishingly small. The story of the far future is told in numbers so large that they cannot be spoken in ordinary terms, only described. So let us walk it slowly, stage by stage, and let the silence deepen as we go. The first chapter of the far future belongs to the stars, and it is already past its peak. Star formation across the cosmos reached its height billions of years ago and has been declining ever since. The universe is running low on the cold gas from which new stars condense, and as that gas is used up, fewer and fewer new suns will ignite. In roughly 100 trillion years, the last star will form from the last available gas, and after that, no new stars will ever be born again. The existing stars will live out their lives, the bright massive ones burning fast and dying in mere millions of years, the small dim red ones husbanding their fuel for trillions of years more. The longest-lived stars, the faint red dwarfs, will glow on quietly, cooling and dimming, until even they exhaust themselves. And then, after a span of time so long that the present age of the universe is less than 1,000% of it, the last star will flicker and go dark. The era of starlight, the era we live in now, the only era in which planets are warmed and life as we know it is possible, will end. This is the chilling reality of cosmic time. The age of stars feels permanent to us because every star we have ever seen has burned steadily across all of recorded history. But on the true scale of the future, the age of stars is a brief opening flash, a single bright morning at the start of an endless night. After the last star dies, the universe enters a long darkness, lit only by the faint fading glow of stellar corpses, the white dwarfs and neutron stars cooling slowly toward absolute zero, radiating away the last of their heat into the expanding void. There will be no sunlight anywhere. The galaxies, by now isolated islands cut off from one another by the expansion, will each become a graveyard of dead and dying stars, drifting in a darkness deeper than any night that has ever fallen on Earth. But even the dead stars do not last. Over spans of time longer still, the cold remnants will be ground down by processes so slow they can barely be called events. Some will collide, some will be flung out of their galaxies entirely by chance gravitational encounters, sent drifting alone into the intergalactic dark, and over almost incomprehensible stretches of time, matter itself may begin to decay, the protons at the heart of every atom slowly dissolving, if certain theories are correct, until ordinary matter simply ceases to exist. The honest answer is that nobody knows for certain whether protons decay, and if they do, It happens over a span of time so vast that the number of years would require more than 30 digits to write down. But if it does, then eventually there will be nothing left of stars and planets and the stuff of worlds at all. Only the most extreme objects will remain. Those objects are the black holes, and they inherit the universe. After the stars are gone and ordinary matter has dispersed or decayed, the black holes endure, vast dark regions of trapped gravity, the last great structures in a hollowing cosmos. For an enormous span of time, they will be the only significant objects left, slowly swallowing the rare scraps of matter that wander too close, growing in lonely silence. And it would be natural to assume they are eternal, that these are the permanent monuments of the dead universe, the one thing that lasts forever. But they are not. In 1974, the physicist Stephen Hawking, working at the University of Cambridge, made a discovery that astonished even himself. Black holes are not perfectly black. Through a subtle effect at the boundary of the horizon, where the quantum foam of empty space meets the edge of the trap, black holes very slowly leak energy into the surrounding void. They radiate. They evaporate. Over time they shrink. And eventually, after a span of years so long that it dwarfs every number we have yet spoken, they vanish entirely in a final faint flicker of radiation. Now, extend that calculation across the full sweep of deep time, and you reach the final chapter. The largest black holes, the supermassive giants at the hearts of galaxies, will take a span of time written as 10 followed by roughly 100 zeros to evaporate completely. That is the longest meaningful event in the projected history of the universe. And when the last black hole has evaporated, there is nothing left to happen. No stars, no planets, no matter, no structure of any kind. Only a thin, ever-thinning bath of radiation, stretched by the endless expansion toward longer and longer wavelengths. Colder and colder, fainter and fainter, approaching but never quite reaching absolute zero. The temperature of the cosmos will fall toward a stillness so complete that no event can occur, because every event requires a difference in energy, and in the final state there are no differences left. Everything will be the same everywhere. This is what physicists call the heat death of the universe, and despite the name, it is not hot at all. It is the coldest, stillest, emptiest condition that the laws of physics permit. It is the universe at perfect rest, forever. Physicists who study the deep future often divide it into great ages, each one longer and darker than the last, and walking through them slowly is the surest way to feel the true scale of what lies ahead. The age we live in now is called the stelliferous era, the age of stars, the time when the cosmos is filled with light, because stars are forming and burning across countless galaxies. It began a few 100 million years after the beginning, when the first stars ignited, and it will continue for perhaps 100 trillion years, until the last star forms from the last cold gas, and the last red dwarf finally gutters out. To us this age feels eternal, because every star in every record of human history has burned without interruption. But measured against what follows, the age of stars is the briefest chapter of all, a single bright opening paragraph in a book, whose remaining pages are written almost entirely in darkness. After the stars die comes the degenerate era, the long age of stellar corpses. The cosmos will be populated by the cold remnants of dead stars, the white dwarfs slowly fading, the neutron stars cooling, the failed stars too small to ever have shone, all of them drifting in the dark and radiating away the last traces of their warmth. There will be no new light. The galaxies, by now isolated beyond any horizon from one another, will be vast dim graveyards. If protons decay, as some theories predict, then across spans of time written with more than 30 digits, even these cold remnants will slowly dissolve, their matter evaporating particle by particle, until the ordinary stuff of stars and worlds has ceased to exist. The honest truth is that we do not know whether protons truly decay, and so we do not know exactly how this era ends, only that it ends in deeper darkness than the one before. Then comes the black hole era, when the only significant objects remaining are the black holes, inheriting a universe emptied of nearly everything else. They will be the last great structures, dark and silent, slowly leaking energy through the faint Hawking radiation that Stephen Hawking predicted in 1974. Over spans of time so vast that the entire previous history of the cosmos rounds to nothing against them, the black holes will shrink and evaporate. The largest of them will last for a time written as 10 followed by roughly 100 zeros, before vanishing in a final faint flicker. And after the last black hole is gone, the cosmos enters the dark era, the final age, in which nothing is left but a thin and ever-thinning haze of radiation and stray particles, stretched colder and fainter by an expansion that never stops. It drifts toward a stillness so complete that time itself loses any meaning, because nothing ever changes again. This is the destination written into the equations. Not fire, but cold. Not a bang, but an endless, silent, perfect dark. And here, at last, is the deepest meaning of why nothing can ever escape the observable universe. We began with the idea of a prison, a boundary that traps us inside a region we can never leave. But the true picture is far stranger and far more solitary than a prison, because a prison at least implies a world outside, a place the walls are keeping you from. In the far future, there is no outside left to reach. The other galaxies will not merely be unreachable, they will be gone from our sky entirely, red-shifted into oblivion, while our own merged galaxy slowly burns out and dissolves into the cold. The walls of the observable universe close in, not on a captive longing for freedom, but on a stillness where there is nothing left to long for. The expansion does not merely seal us in, it empties out everything we might have wanted to escape toward. There is, within all of this, the smallest seed of something that is not quite hope, but is not quite despair either. The timescales are so immense that they almost lose their power to frighten. The last star will not die for 100 trillion years. The last black hole will not evaporate for a span of time with 100 zeros in it. Against numbers like these, the entire history of life on Earth, the entire span from the first living cell to this very moment, is less than an instant, a single spark struck in the dark and gone before the night truly begins. And we are alive now, in the bright morning of the cosmos, while the stars still burn and the sky is still full of galaxies, and the evidence of where we came from is still written across the heavens for anyone patient enough to read it. We did not arrive too late, when the book had already been erased. We arrived early, in the one brief window when the universe is still legible, still luminous, still generous with its light. The cell is vast beyond measure, and for now, it is full of stars. Whether that is a comfort or a sorrow is not a question that physics can answer. It is a question that belongs to us, to the strange brief flicker of awareness that the universe has somehow produced in the middle of all this cold machinery. And it is to that question, the only one the equations cannot touch, that we now finally turn. For all of human history, we have told ourselves two opposing stories about our place in the cosmos. And the strange truth is that the science of the expanding universe supports them both at once. Perhaps the lesson of the closing horizon is one of profound smallness, a reminder that we are a momentary chemical accident on a single grain of rock, briefly aware, in a universe that is vast and cold and entirely indifferent to whether we exist at all. It is a universe that is even now drifting beyond our reach, and that will one day forget that we were ever here. Perhaps the honest response to a cosmos that seals us in and empties out around us is a kind of quiet humility, an acceptance that we are far smaller and far more temporary than we ever wished to be. Or perhaps the lesson runs precisely the other way. Perhaps the fact that the universe is closing, that the window of knowledge is finite, that we happen to be alive in the one brief epoch when the whole story can still be read, makes our existence not smaller, but almost unbearably precious. Perhaps a thing that cannot last is worth more, not less, because it cannot last. These questions have no universal answers, and they were never meant to. Different people, looking at the same cold equations and the same fading galaxies, will feel entirely different things and each of them will be right in their own way. Some will find in the heat death of the universe a reason to despair, and some will find in it a reason to cherish the morning while it lasts. Some will look at the unreachable galaxies and feel the bars of a cage, and some will look at the same galaxies and feel grateful that they can be seen at all, even from behind glass, even for a little while. The universe does not instruct us how to feel about it. That choice, perhaps the only true freedom we have inside the closing horizon, belongs entirely to us, and so it is worth holding the whole picture in your mind, all at once, before you drift off to sleep. You exist on a small blue world orbiting an ordinary star in an ordinary galaxy, inside an observable universe that stretches 93 billion light-years from one edge to the other. It holds within it nearly 2 trillion other galaxies, almost all of them already racing beyond any hope of contact, almost all of them destined to vanish from the sky in the long ages to come. You are a brief arrangement of atoms that the cosmos assembled out of the ash of dead stars, atoms that have somehow learned to look up and measure the very expansion that is carrying everything away. The same universe that seals you in has also, against all odds, woken up inside you and is using your eyes to watch itself drift apart. That is either the loneliest fact in all of existence or the most extraordinary one. Most likely it is both, and they were never truly separate. Nothing can escape the observable universe. The galaxies cannot return, the horizon cannot reopen, and no ship we could ever build will outrun the growing dark. But that is not the end of what can be done within these walls, and the walls are wider than any imagination can hold. Inside this closing horizon there is still room for every story that has ever been told, and every story that ever will be. Room for the entire history of love and curiosity and discovery. There is room for 100 trillion more years of starlight before the long night falls. The universe is leaving, but it is not left. The light still arrives. The sky is still full. So close your eyes now and let the cosmos drift where it must. The galaxies are slipping away, one by one, silent and slow, beyond any door we could ever reopen. But they have not all gone yet. The stars above you are still burning, the light is